We're going to take notes in our science notebook today and start a lab. So if you will, in your table of contents, write freezing, melting, boiling point, ... page 30. Then write classifying matter, page 31 through 33. All right, so we're going to go to freezing, melting, boiling point first. So you're going to find this page right here that's in your paper clipped thing of notes. And then you're going to write, let's see, what page is this? 29 on it. So we're going to write page 29 wherever you're keeping up with your page numbers. So if you will notice, this thermometer right here says freezing/melting point. And this is a Celsius scale because you can see it says degrees Celsius on it. So you're going to shade this thermometer to 0 because the freezing/melting point is 0 degrees Celsius. That's the temperature at which water freezes or melts, 0 degrees in Celsius. Also put 0 degrees Celsius on here in case you're unsure what that was shaded to. So there are two temperatures that we can measure how hot or cold something is in, the Celsius scale and also the Fahrenheit scale. So you need to know that water freezes or melts at 0 degrees Celsius, but it also freezes or melts at 32 degrees Fahrenheit. Now you're not going to shade this thermometer to 32 because it is a Celsius thermometer, but you do need to write 32 on it. The next one is room temperature. So room temperature is about 22 degrees Celsius. So if you look at these, they're counting by tens, 10, 20, 30, 40, 50, and we want to go to 22. So that's 10, 20, and a little bit higher than 20. We're going to shade that in and put 22 degrees Celsius. The last one is the boiling point of water. So on the Celsius scale, the boiling point of water is 100 degrees. So you're going to shade your thermometer all the way to 100 degrees. You can do this in a pencil or a crayon, totally up to you. I'm using a pen just so it shows up better on the camera. So that's 100 degrees Celsius, or it is 212 degrees Fahrenheit. Notice I didn't give you the Fahrenheit for room temperature. You don't have to know Fahrenheit for room temperature. You actually don't have to know room temperature at all. But you do have to know the freezing and melting point in Celsius and Fahrenheit, the boiling point in Celsius and Fahrenheit. These will be on your test, the freezing and melting point and the boiling point in both Celsius and Fahrenheit. So start studying them now. Your test isn't going to be for like a couple more weeks, but start studying them now. There are a couple of more things that we need to put on this. So you can draw an arrow to the top, you can draw an arrow to the bottom. Let's see, I'm going to draw an arrow to the bottom here, which means I need to move my notebook so you guys can see what I'm drawing. All right, so we need to define what freezing means and what melting means. So down here, we're going to put freezing. When liquid water becomes solid. When liquid water becomes solid. All right, we also need to define melting. So we're going to write melting. Melting is when solid becomes liquid water. So melting is like when you have ice and it turns into water. Freezing is when you have water and it turns into ice. one more that we need to define, and this time I'm going to go to the top, and that is going to be the boiling point. So I'm going to draw an arrow up here to define boiling point. So I'm going to write boiling. When water becomes a gas. All right, so when you have the boiling point, you're having water changing into gas. Now, the other thing that we wrote in our table of contents was classifying matter on pages 31 through 33. So you're going to find this page here in your notes, glue it down on page 30, and make sure that you write page 30 wherever you're keeping up with your page numbers. Then you're going to find this page here, which is part 2 of this lab. You won't do part 2 until tomorrow. You are doing part 1 today. And you will write page 31 wherever you're keeping up with the numbers on that page. And then finally find this page, which is part 3 of the lab, and you will write page 32 wherever you're keeping up with those numbers. Okay, this part 3 is going to get done Wednesday, and you have a bag of supplies in order to do that. This part 2 is going to get done Tuesday, and you have a bag of supplies in order to do that. And this part 1 is actually going to get done right now. So after you glue page 30, 31, and 32 down in the correct order, and you number those pages, you need to focus on this page for the rest of the video. All right, today we're going to do the classifying matter part 1 lab. So in front of you, I have 3 beakers of different forms of water. So in the first beaker, there's ice. It's 250 milliliters. It's filled up to the 250 milliliter line. In the second one is water, and that's filled up to 250 milliliters. And the third one is water, but we're actually going to pour this one into this pot right here. And we're going to boil it to make water vapor. So let's turn the stove on. There we go. All right, so now we are going to take the temperatures of the ice and the water. Now, if you were doing this at home, it's very important that the thermometer you can see is in the middle of the ice, because you want to get the temperature of the ice. You don't want to get the temperature of the graduated cylinder that it's in. So if I take this thermometer out, you can see it's right there. The red line is right there, which is at 0. This is a Celsius thermometer. The C is right up there for Celsius. So it's 0 degrees Celsius because that's how cold the ice is. Now we're going to look at the temperature of the water. Now the thermometer here is resting on the bottom of the graduated cylinder, so that's really not a fair reading. I'm going to hold it out. I'm going to hold it up for a minute so it's just touching the water. So part of this lab is to look at the temperatures of ice, water, and water vapor, which we'll have to wait a little bit for that water to boil before we can get the temperature of water vapor. The other part of this lab is to see when this ice melts if there is still 250 milliliters of water left in the graduated cylinder. So make a prediction. Do you think in a few hours when this ice melts that it will still be 250 milliliters? We shall see. All right, so I've been holding this up long enough. See if I can get this quickly so I don't heat up the thermometer. So it's right below the 20. So it's about 18 degrees because each of those lines it counts by 2s. That's 10, 12, 14, 16, 18. So it's about 18 degrees Celsius for the water, and it was 0 degrees Celsius for the ice. So you can record that on your notebook page for classifying matter part 1, and then through the magic of time-lapse video, we will cut to the next part where this water is boiling, and we'll take it to the temperature of that as well. So as you can see, our water is boiling now, and we want to take the temperature of the water vapor, which is the steam that is rising from the boiling water. So we hold the thermometer right above the water. We don't hold it into the water. We don't want to take the temperature of the pot. We want to hold it right above. And then if we look at the temperature, and yes, I'm holding this with a pot holder because it really hurts, and the steam, I don't know if y'all can see that, but it is right at 100, and now my other hand that's holding the phone is hurting. So the temperature of water vapor was 100 degrees, and you can watch as soon as I take it out of the water, see that red line start to go down because it's out of the water. See? So the temperature of the water vapor was 100 degrees. The temperature of the plain water was 18 degrees, and the temperature of the ice was 0 degrees Celsius. Now, we are waiting on this ice to melt to see if the volume of the ice changes. We are also going to see if the volume of this water changed. Do you remember how much water I poured in this pot? It was 250 milliliters. All 3 beakers started out with 250 milliliters. So we're gonna wait for this water to cool down some. I am gonna put the lid on it so the steam will be kept in there. Ow, ow, ow. But we're gonna wait for it to cool off because I don't wanna melt this graduated cylinder here. And then once it cools off, we will pour it in here and see if it is still 250 milliliters. So our water has cooled off now. We're gonna pour it back into the graduated cylinder to see if we still have 250 milliliters. I am using a funnel so that hopefully I don't make a colossal mess. Let's see what happens. There we go. All right, so we have about 152 milliliters of water. So where did all that water go? There might be a couple of drops left in the what is this called? Left in the funnel. There might be a little bit of drops left in the pot, but not enough to make up the 100 milliliters that were missing. So where did it go? It evaporated. That was all the steam that we saw rising from the pot when we were taking the temperature. So it's in the air now. Even though we can't see it in the air, that is where it went. So the volume of the water did go down because it went into the air. All right, now we have our graduated cylinder that did have ice in it. You can see, hopefully, that there is still some small chunks of ice, but Miss Bridges is really tired and ready to go to bed, so she's tired of waiting for it to melt. So we're gonna go ahead and look at it, and that is a little less, let's see, that's 126-ish, I think. So that's about 126 milliliters, and we did have 250 milliliters. So where did the ice go? I mean, ice is just water in its solid state, right? So why is it that when it was ice, it was 250 milliliters, but now as a liquid, when it melts, it's only, what'd I say, about 126? And so it takes up less space in its liquid state than it does in its solid state. Also, if you remember from when we had ice in here, there was a bunch of little air pockets all around, okay? It was crushed ice, but not every single solid space was filled up with the ice, because it's impossible to do that because of the shape of the ice in its solid state. I hope you filled this out with the video, but in case you didn't, here is what you should have done while you were watching that experiment that I did at my house. The temperature in its solid state at ice was 0 degrees Celsius because that is what the thermometer measured in. But I also want you to put 32 degrees Fahrenheit because we need to know both. The liquid that wasn't frozen was 18 degrees Celsius. And then the gas or the water vapor was 100 degrees Celsius, which is also 212 degrees Fahrenheit. In all 3 instances, I started with 250 milliliters of ice, liquid, or water to make water vapor. Did I end all 3 with 250 milliliters? No. The only one I actually ended with 250 milliliters was the liquid one. Constant shape. The solid, yes, it has a constant shape. The liquid, it takes the shape of its container. When I took that liquid from the graduated cylinder and poured it into the pot, first it looked like the graduated cylinder, and then it looked like the pot. But if I took the ice and poured it into the pot, it's not going to look like the pot. It's still going to look like the ice. And then the water vapor, it takes the shape of its container as well, which we didn't catch it and put it in a container. It just went into the air. The drawing of the particles, the solid particles should be all tightly packed together. The liquid should be moving past each other slightly. And then the gas is a lot of space in between because they move freely. And that goes into the movement of particles. These particles move very little because they're so tightly packed. I always like to do this demonstration with my hands when we talk about the states of matter and the particles. So for a solid, if you take your hands and you put them together and you squeeze really, really hard, so you can't, if you're squeezing, you can't really move your fingers, right? So you can actually see how my knuckles are turning white. I'm squeezing so hard. So my fingers, which we're using to represent the particles of the solid, I can't really move them. They can vibrate a little, but it's very, very little. Then in a liquid, to represent a liquid, so now you're going to hold your hands together, but instead of squeezing so hard, you're just going to hold them together. Well, now I can move my fingers, right? So they can slide past one another. So that is why the particles in a liquid slide past one another. And then finally, gas, they move freely. So the gas is like this. If these particles in a gas, they're just like, woo, having a party. Okay? So this is what your chart should look like. If you need to go back and revisit the video or the earlier in the video, you may. And now you need to answer these 3 questions by yourself. So these were discussed in the video. You can go back and make sure that you answer them. If you leave them blank, you're going to get points deducted when I do my next notebook check. Please don't leave them blank.